Hi, in this video, I will be showing you problem number 13 of chapter 12, section 6. Use traces to sketch and identify the surface. X square equal to 4y square plus z square. So first, we have to do all the three traces, namely yz trace, xy trace, and the xz trace. So let's consider first yz trace. Yz trace is the trace by looking at the curve of intersection of the surface on the plane x equal to constant, which is a plane parallel to yz plane. So we are going to plug in x equal to k into the original equation given in the problem. So x is replaced by k. So it could be positive k or negative k because we have anyway x square. So it doesn't matter. So k could be positive or negative. So then we get k square equal to 4y square plus e square, which is k is after all a constant. So if you divide the whole thing by the constant k square here, then we can bring it to the form of an ellipse. So it is an ellipse on the plane parallel to the yz plane, which is on the plane x equal to k. As an example to a value for k, we will give a value for k, let's say x equal to k equal to 2. So we are looking at a plane parallel to yz plane at a distance 2 from the origin on the x-axis. So it is a plane parallel to yz plane at a distance 2 from the yz plane. So we're going to plug in a specific value here, k equal to 2. So we get k square, which is 4 equal to 4y square plus e square. So if we divide everything by 4, we get y square over 1 plus z square over 4 equal to 1, which is an ellipse in the yz plane, cutting the y axis at plus 1 and negative 1, cutting the z axis at plus 2 and negative 2. So this is an ellipse in the plane x equal to 2, which is a plane parallel to yz plane. So if we draw just a two-dimensional graph, this is a two-dimensional graph where we consider only yz axis as opposed to xyz axis. So this is a trace. The traces are all in the two-dimensional planes, or in traces which are parallel to the coordinate planes. So ellipse on the plane x equal to 2. So this is the same when x equal to negative 2 also. So on either side of the x-axis, you have an ellipse which is parallel to the yz plane. Let's assume in the same case, k, what happens when k equal to 0 though? So when k equal to 0, by substituting into the original, we get 4y square plus e square equal to 0. Sum of two squares cannot be 0 unless each one of them is equal to 0. So we get y equal to 0 and z equal to 0. This tells us that x equal to 0, y equal to 0, and z equal to 0 is a point on the surface. So origin lies on the surface. So now if k is less than 0, then also we get the same ellipse, k square equal to 4y square plus z square. So k is positive or negative, or in other words, on either side of x-axis, we get the families of ellipses. The trace is an ellipse on the plane x equal to k, and also on the plane x equal to negative k. K can be anything on there. So on either side of x-axis, we have ellipses. Now let's do another trace. So let's consider y equal to k, which is the xz trace. Or on the plane parallel to xz plane, what is the trace is what we are going to find out. So if we substitute a generic value k into the original equation x square equal to 4y square plus z square, we get x square plus 4k square plus z square. So if you move the z square to one side, you get x square minus z square equal to 4k square. The right hand side is a constant. So we can use, we can have some constant on the right hand side. If we divide the entire thing by that constant on the right hand side, we can make the right hand side to become 1, which is obviously an ellipse, obviously it is a hyperbola. So this is a hyperbola on the xz plane for all values of k not equal to 0. For k not equal to 0, positive or negative. So now, if k equal to 0 though, we get x square minus z square equal to 0, which means that x square equal to z square. That gives us x equal to plus or minus z, which are two intersecting lines passing through the origin. So when k equal to 0, we get two intersecting lines passing through the origin on the xz plane. As we did in the previous case, we will just give an example we'll take a value for k and then see what happens to the actual hyperbola. So let's say, give an example, let's say k equal to 1 in this case. So if you substitute back into the original equation, so we get x square equal to 4 plus 4y square plus z square. Into this, if you substitute y equal to 1, we get x square minus z square equal to 4 times 1. So if you divide everything by 4, you get x square over 4 minus z square over 4 equal to 1, which is a hyperbola on the xz plane. So cutting the x at 2 and negative 2. So x square over 4 minus z square over 4 equal to 1 is a hyperbola. We can graph this. So this is intersecting the x-axis at 2 and negative 2, and the z-axis at 2 and negative 2 as well. So if we graph this hyperbola, and then we can also see the asymptotes of this hyperbola, which are x equal to plus or minus z. So we graph this. So these are hyperbolas. So this can be done for every value of k. We gave an example for k equal to 1. For y equal to 1, then it could be y equal to 2 plus or minus 2 plus or minus 1. So on either side of the y, which is parallel to xz plane, the trace is a family of hyperbolas. Now let's find out the xy trace by taking z equal to a constant. So if we substitute that into the original equation, we get x square equal to 4y square plus z square, where z is equal to k here. So x square minus equal to 4y square plus k square. So if you move the y square to one side, so x square minus 4y square equal to k square. If you divide the entire thing by k square, you will get a hyperbola in the xy plane. Or in other words, it is in the plane parallel to xy plane, which is a horizontal plane. The traces are all hyperbolas. Which is a hyperbola in the plane parallel to xy plane, or in the plane z equal to k, and this is true for k not equal to 0, but k can be positive or negative. So when k equal to exactly 0 though, you get x square minus 4y square equal to 0. If you solve for x square, you get x square equal to 4y square, which would mean x equal to plus or minus 2y. So again, two intersecting lines passing through the origin. Now let's take an example and give a value for k. Let k be equal to 2 again. Let z equal to k equal to 2. So we are looking at a plane parallel to xy plane, horizontal plane at a distance 2 from the origin, from the xy plane. So if you substitute that into the original, you get x square minus 4y square equal to 4. By dividing entire thing by 4, you get x square over 4 minus y square over 1 equal to 1, which is pretty much a hyperbola intersecting the x-axis at 2 and negative 2. So it's a hyperbola in the plane z equal to 2, this is just an example. So every horizontal trace is going to be a hyperbola. So you get family of hyperbolas in the horizontal planes. Now x square over 4 minus y square over 1 equal to 1. We will trace this in the xy plane in the two-dimensional, this is a two-dimensional trace. So we consider only xy plane or parallel to xy plane at a distance z equal to 2. So we graph this hyperbola, we get x is intersected at 2 units and y intercept is 1. So you complete this rectangle and join the diagonals, and then you draw the hyperbola crossing the x-axis at 2. So these asymptotes are x equal to 2y, so y equal to half of x and y equal to negative 1/2 of x. So which is a hyperbola, and this is xy trace is a hyperbola now. So what is the conclusion so far? So initially we said and the YZ trace is an ellipse. Then we said XZ trace is a hyperbola. And now we are saying XY trace is a hyperbola also. And then origin is a point on the graph, on the surface. And then two intersecting lines which are x equal to plus or minus z on the xz plane, and also we saw another intersecting lines when k was equal to 0, x equal to plus or minus 2y. These are two lines in the xy plane, and also on top of that we proved that origin is a point on the graph. And then you get ellipses on either side of the x-axis. Okay. So the final graph can be given as follows. So let's draw the xy-z axis now. And then we'll show the ellipses and the cone. So it is going to be a conical type. So where we have, so at x equal to 2 plane, and x equal to 2 and negative 2. So this is 2 and this is going to be negative 2. X equal to negative 2. And that plane, you are going to have an ellipse. That's what we showed in the beginning. And then the other traces are all going to be hyperbolas, and then you're getting those intersecting lines as well. So this is the shape of the final graph. The final graph we also mentioned that 0, 0, 0 lies on the graph, and it's called an elliptical cone. The surface is called an elliptic cone. Hope this video helps.